Alright, 2016 number 1. Hopefully you're watching some of these videos, and if you go through these FRQs and you're like, got it, don't have to look, then God bless you, you're doing great. But if you're working through them and then you're checking the videos and checking your answers with them, I think that's extremely beneficial, just to catch little things along the way, even if you feel like you're getting the answers right. So we're going to fly through this one. This starts, a student is investigating enthalpy of a solution, delta H, for these two different things. They have a calorimeter. It's a good indicator. We're using Q equals MCAT, a balance, and a thermometer. And so they want to measure delta H of the solution. We're given 100 grams of water, initial temperature. We're dropping 10 grams of lithium chloride. It's dissolving, and they're given a new temperature. So we have a change in temperature, and we have a mass of that solution. This says calculate the magnitude of the heat absorbed in the solution, assuming the specific heat capacity. Man, if you are given specific heat capacity, or Q equals MCAT, they give it for the solution, right? So that's the total mass of the water plus the 10 grams of lithium chloride. That is just the heat capacity of water, but they've said solution here, so you have a cumulative mass there. So 100 grams of water, 10 grams of lithium chloride. This guy looks like this. 110 grams. It gives us a specific heat. That's our constant, 4.18. Careful units here. That is joules over grams times degrees Celsius. They fed us the unit on that thing. Kelvin or Celsius doesn't really matter here. And then we need a change in temperature. We have a final temperature, 35.6, an initial temperature of 15. And so we've got a change in temperature here of 20.6 degrees Celsius. Our units all cancel except for our joule unit. And we can solve for our Q value here in this problem. Should be, it's 9,470 joules, or 9.47 kilojoules. That's how much energy is given off there. Either way on the sign on that thing, make sure you put units. What's it ask for unit wise? Doesn't matter. So you can put either unit here. I put kilojoules because I'm anticipating the next problem, or next part of the problem says delta H in kilojoules per mole. So here we go. So this says determine the value of delta H. This is part 2. That's it for part 1. You get a point for a unit. You get a point for the answer there. And then part 2 says determine the value of delta H for lithium chloride in kilojoules per mole. This is kilojoules per 10 grams. So in part 2 we've got to take our 10 grams of lithium chloride and we've got to turn it into how many moles of lithium chloride are we dealing with there. And so we add them above the periodic table, 42.4 grams per 1 mole. And that gives us 0.236 moles of lithium chloride. And so easy enough, 9.47 kilojoules, how much heat energy is given off, divided by the number of moles that are dissolved there. And that will tell us that we have 40.1 kilojoules per mole released. It's released. It should be negative there for our delta H. Be careful of signs when they're delta H's. Should be a negative. So you got a point for the number of moles of lithium chloride in this guy. You get a point for having the right answer with the negative sign. You got to, it's delta H, you got to put whether it's positive or negative for the Q value. Then we're to the second piece. It says to explain why delta H for NaCl is different than lithium chloride, student investigates factors that affect delta H. Finds that radius and lattice enthalpy, or delta H, is associated with the solid crystals going into gas. They contribute. The student consults references, collects data. So they give us a little data chart about radius of the elements. They don't need to give us this data chart. We should already know lithium is smaller than sodium because lithium is farther up on the periodic table in that group of alkali metals, which means it's farther up, it has less energy levels. And so B says, write the complete electron configuration for the sodium ion using the ground state. You will have an electron configuration to write on the AP exam. I'm almost guaranteeing it. You'll probably have Q equals MCAT. It's shown up several times the last 4 or 5 years. And so B says, write the electron configuration for the ion of sodium, Na+. And so you peek at the periodic table. This is 1s2, 2s2, 2p6. Sodium has, the element sodium has 11 protons, and so it normally ends with 3s1, except this is the sodium ion, which means it's lost that 3s1 electron to make it like a noble gas. That's it. That's our electron configuration there for the sodium ion. That's it on B. It's a free point. We got to get that one. Then it says, using principles of atomic structure, explain why the sodium ion is larger than the lithium ion. We just talked about that unintentionally. I talked about them giving us the radius, right? And this is asking, why is sodium ion larger than the lithium ion? So sodium ion is larger than lithium because there are additional energy levels moving down the groups on the periodic table. You can put, therefore, more electron shielding and bigger radius. Just like that. Part D. Part D says, which salt, lithium chloride or sodium chloride, has the greater lattice enthalpy? Justify your answer. Lattice enthalpy, how much energy it takes to break that crystal lattice apart, or how much energy is released when that crystal lattice forms. Either way, the greater one is going to belong to lithium chloride. So it asks that, which salt? Lithium chloride. Answer the question. Why? According to Coulomb's law. This is a Coulomb's law question, where the energy there is proportional to the charges Q1, Q2 over the radius. The charges are the same on lithium chloride and sodium chloride. They're both 1 charges. The radius makes the difference here. And so because lithium is smaller, it has more lattice energy. lithium, you can write this if you wanted, lithium's nucleus can get closer to the chloride. That's part D. And then part E, we're almost done writing sentences on this. Part E says, below there's a representation of a portion of a lithium chloride crystal. Identify the ions in the representation by writing the appropriate formulas, lithium or chlorine, in the boxes below. Lithium has lost an electron, which generally makes it smaller. Chlorine has gained an electron, which makes it bigger because it has more repulsive forces, and that applies here. Lithium is the smaller one. You can also look at the trend on the periodic table, or even look at the noble gas that this corresponds to. That's like helium. This chlorine is like argon, and so chlorine's going to be bigger here, and so the bigger one belongs to chloride. The smaller one belongs to lithium. It says identify the ions, write the things with charges. Don't just put Li and Cl or you get popped for it. And so those guys are your answers to E. It's another little free point. Just pay attention to what you're doing there. Those are they're not, I lied. All right, good. And then the last one, F, says the lattice enthalpy of lithium chloride is positive, indicating that it takes energy to break apart the lithium chloride. Perfect. However, the dissolution, the dissolving of it, is exothermic. Identify all the particle interactions that contribute to the exothermicity of this thing. When you've got lithium chloride and you want to dissolve it in water, the first two steps of this are endothermic. We've got to rip the lithium and the chloride charges apart. We've got to take all these water molecules that were really close together and we've got to pull them farther apart. Those are both endothermic. This is not answering the question, but those are both the endothermic parts. You got to stretch the lithium chloride and stretch the water. The payoff here is that at some point that lithium ion is going to be surrounded by water molecules this way. And the chloride is going to be surrounded by water molecules with their hydrogens closest to the chloride ion. I'm doing a terrible job of the drawing here, but hopefully you'll get the point. So they're surrounding them. These two are both exothermic, where the negative oxygen is attracted to the positive lithium and the positive hydrogens on the water are attracted to the negative chloride. And so those are the two forces that we are talking about here that are exothermic. So for each of those interactions, include the particles that interact and the specific type of intermolecular force. What we have here is some ion interactions between the polar water molecules and those ions. These are ion dipole interactions. So I would put both lithium ions to water and chloride ions to water are ion dipole interactions. Just call them what they are, right? That's polar, so it has dipoles on it. So that's an ion dipole interaction. Hopefully my video is not bobbing the whole time y'all are watching it. Y'all are gonna seasick watching it. But that's it. That's our answer. Both lithium, these are the exothermic parts. Those are the endothermic parts. They always occur this way when you're dissolving something. Break apart the solute, break apart the solvent, both positive delta H's, and then the exothermic part that they ask about here is the ion dipole interaction between those two things. Hope that helps. That's number 1 on 2016.